This is Dr. Fang. Today we talk about chapter 3, vectors in physics. Okay, so we'll learn what is vectors in detail. So in this chapter, we'll learn scalars versus vectors. Okay, so basically there are two kinds of physical quantities, scalars and vectors. So what's the difference between them? Other than that, we'll learn everything about vectors, the components of a vector, adding and subtracting vectors, units of vectors. Okay, after we learn everything about vectors, then we will talk about position, displacement, velocity, and acceleration vectors. Last chapter we actually learned about everything about this. However, um, this chapter is prepared for two-dimensional motion. Okay, so for two-dimensional motion, we have to use vector notation to describe a position, displacement, velocity, and acceleration. Okay, and at last, we talk a little bit about relative motion. Relative motion is very interesting. Einstein, so now we know after 1900, we have something called relativity, special relativity, and general relativity. Where relativity come from? Relativity comes from relative motion. So today we talk a little bit about relative motion, and which may give you some interest about this part of motion. All right. So first, let's talk about scalars and versus vectors. So what is scalars? A scalar is a physical quantity, usually with a number, with a unit. Okay, so the physical quantity. This kind of quantity we call the scalar. For scalar, you only have a number with units. Okay, well, units is important, right? So from units, we can tell what kind of physical quantity it is. Okay, without units, number is number. No physical meaning at all. Okay, so for scalar quantities, you only have a number, okay, with a unit, right? Nothing about the direction, just number. So for the physical quantities, give you an example, temperature. T is a physical quantity. Okay, so today temperature is about what, 90 degree Fahrenheit. Okay, so there's a number and the quantity. If it's very cold, then negative 20 degree Fahrenheit. Okay, so negative number, just a number with a unit, right? So temperature is a scalar, mass is a scalar. Okay, so we'll learn what is mass later in Newton's law. Okay, density. Density is a amount of matter per unit volume. That is a scalar. Okay, and the time interval. Okay, from now to what time later, right? So with maybe 10 minutes later. Okay, so time interval here is 10 minutes. Okay, just the time interval is a scalar. So for scalar, it's just a number with a unit. Okay, can be positive, can be zero. Number can be positive, can be zero, can be negative. Okay, so that's a scalar. Well, another kind of physical quantity is called a vector. So what is a vector? Okay, vector always come with two components, magnitude and direction. You always have those two components. Magnitude is a positive number. Remember, it might be a positive number with a unit. Okay, come with the units, right? Direction tells you which direction it's going. So you have a directional social vector with a vector. Okay, so if you talk about, so last chapter we actually talk about velocity of the vector, right? So 20 meter per second, that is magnitude of that velocity. Direction, well, north. Okay, so you know that is a vector, that is a velocity vector. It's a vector come with a magnitude and a direction, equally important. Okay, without direction, that is not a vector. Okay, so you have a direction come with the vector, come together, magnitude and the direction, they always come together. So last chapter we talked about speed. Speed is a scalar. There's no direction. Velocity is a vector. So the magnitude of velocity actually is a speed. Okay, so that is speed, right? So velocity is a vector. Magnitude of a velocity that's a speed. Okay. Well, let's see an example. So this diagram tells you here is your location, right? So you want to go to library, okay? So the distance, library is from you, and library is 0.5 mile. You can tell, right? And direction is important, okay? So which direction you go, you see? So this is where you go, where your location, right? Suppose library, there's somewhere is library, right? Assume here is library, right? And last chapter we talked about displacement, starting point and the final ending point, right? You draw a line, connect them together, right? So that is a changing position is displacement. Okay, equal to final position. Well, in this case, right, I will tell you how to describe a position. However, displacement here is this term, right? So you have to tell, if you go to library, you have to tell, okay, so you're here, library is a 0.5 mile away. If it's here, south, north, east, right? So this direction. Well, if you can go this direction, you have to tell like what angle, right? South due west. Oh, by the way, sorry. So this is northwest, right? So it is northwest direction. So this is west, northwest, right? So this is whatever degree south due west, okay? Or if library is here, 0.5 mile away, 0.5 mile north, south. Okay, direction is so important. Without direction, you really don't know where the library is. Okay, so displacement is a vector. Okay, we'll talk about it later. Okay, so important here is this. Distance, right? It's important. However, direction also important. So distance plus put distance and direction put together is displacement. You can tell where is the library precisely if you give distance and direction. Okay, so so this one tells you that if even you know how far away from the, so if it's you here, library is here, right? So you will know how far away is library, right? And you may not get to the library directly, okay? So if you cannot get directly, you can go 2 segments, right? So from here, you went west for 1, 2, 3, 4, 3 blocks, right? And then you turn north by another few blocks, right? So you can tell how to get a library. Okay, so you have give the distance, direction, and another distance and the direction. Okay, so if you cannot go to library directly, or you can go from here to there directly, so you can tell equivalently this, right? This vector, it is a vector, right? You see direction and the distance equivalent to this vector plus this vector. We call this vector A, this vector B, right? So this is vector C. Well, to represent the vector, you always put an arrow bar on top of vector. So from this diagram, we can tell A vector plus B vector actually equal to C vector. Okay, so this is how you add vectors together. Okay, so the vector, that is a vector, come with magnitude and direction. Okay, so in physics, how do we represent a vector? Okay, here is the way we represent a vector. We use a arrow. Okay, so this is a vector. So you have an arrow or a segment with a arrow, right? With a direction. So basically, this arrow. The length of this arrow tells you the magnitude of vector, and the direction tells you the direction of the vector. So this guy come with two things, magnitude and direction. Okay, so this is a vector. Physics use an arrow tells you vector. Okay, so if I draw a same length arrow with a different direction, so this arrow, we call this arrow A, this is arrow B. Let's assume this is the same length, right? Length is the exact same. So those two are different vectors. Assume this is a velocity vector. So the length stands for 20 meter per second, right? So A vector is 20 meter per second, pointing to northeast direction, okay? And the B vector is, well, you have same length, then it's a 20 meter per second. What? Maybe 30-degree west due north, okay? So you have to tell what direction it is. So that is B vector, okay? So even they have same magnitude, however, they have different directions. So it's a different vector, totally. They're not equal to each other. Okay, so in physics, that's the way we describe a vector. So now what we do here is we can introduce this vector into a coordinate system. Okay, this class will only confine us in two-dimensional coordinate system, which is x and y, right? If it's three-dimensional, then you have x, y, z. So this is only two-dimensional coordinate system. So we can put this vector into a coordinate system. So here, this is vector r. Okay, the magnitude of vector r is 1.10 meters. So this looks like either a position vector. We'll talk about what's a position vector later, or this may be a displacement vector. Okay, this basically tells you position or how far from here to there, right? Okay, displacement. And then you can put this vector into a coordinate system, and this vector comes with a magnitude and a direction. Direction point to that direction. Okay, so point to this direction. All right, so we put this inside of a coordinate system. By the way, coordinate system is up to you. Your preferred. You can build a coordinate system this way, right? So x and y, or if you like, you can go this way, x and y. Okay, doesn't matter. Okay, so anyway, any orientation you like, right? So later we'll learn for physics problem, depends what kind of problem. Okay, so you build your coordinate system at your in the convenient way, at your preference. So we drag this vector inside of this coordinate system. Then what is the angle of this vector, directional vector? Well, we just look at the angle between this vector and the positive x-axis. Okay, so this is the positive x-axis, right? So you have two lines form an angle. And so let's start with the positive x-axis and sweep to the vector, right? Okay, we'll curve to the vector. And then this angle here is we can use this angle to describe the direction. Okay, well you have two ways to sweep from x-axis to the vector, right? You can go this way, you see, right? Go this way, this angle, or you go this way. Okay, this is called counterclockwise. This is clockwise. Okay, we call this CW. This way is called counterclockwise, CCW. Okay, well here's definition. If you go from x-axis to positive x-axis to the vector counterclockwise way, then the angle is positive. Okay, if you go clockwise, the angle will be negative angle. Okay, so in this case, we can tell this vector r, the angle between vector r and the x-axis is 25 degree, which is positive, right? Because you go from x-axis to that vector in a counterclockwise rotation, or this is negative 335 degree if you go clockwise rotation. So you see, you can use angle to describe the direction of vector. Okay, so I say this vector is 1.10 meter magnitude and 25 degree direction. Okay, well, you can tell, right? 25, which means the angle between this vector and the positive x-axis is 25 degree, and you rotate from x-axis to that vector in counterclockwise, right? So you can tell this is the vector. Okay, so I give you another vector, same, right? So which is 2 meter per second, 2.0 meter per second, and I give you negative 45 degree. Okay, so what is the vector is? Will be this vector, right? So you see, you build a x-axis, y-axis, right? And this is negative 45 degree. You see, you can use this way to describe a vector. Magnitude, okay, and direction. This direction is angle between positive x-axis and the vector. However, make sure the sign, if the positive sign, which means you go counterclockwise from positive x-axis to the vector, negative sign, which means clockwise from axis to x-axis to the vector. Okay. All right. Once you get into introduce this vector inside of use of coordinate system, right, to represent the vector. So what you can do here is you can project this vector into x-axis and y-axis. Project means you look at the projection, right? So you see this is your x projection, and this is your y projection. So this is y projection, right? You can move to here. By the way, you can move a vector parallelly to anywhere you like. Okay, so here is a vector, right? Assume this vector, and we can tell this vector maybe this 1.0 meter per second, right? And angle here is 30 degree, right? You can move this vector parallelly to here, to here, another parallelly. Okay, so what is this vector? So this is vector A, right? So this is vector B. What is this vector? Okay, so because you have the same magnitude, right? Same length, which means same magnitude, so 1.0 meter per second. And what direction? You see this direction is 30 degree. Okay, and the same thing here, same magnitude, C vector, right? And the same magnitude, 1.0 meter per second. And if you look at direction, still 30 degree. So you can tell A, B, C, those three vectors have same magnitude, same direction. We call them equal vectors. So A equal to B equal to C. Okay. So now come back to this projection. You project this R to x-axis and y-axis. Okay, and you can tell the projection here is what's called Rx. Rx here is, well, if the vector is 1.10 meter, okay, so the projection in x-axis will be 0.997 meter, and the projection in y-axis will be 0.465 meter, okay. So we can project this vector into two directions, okay, and we call this x component of this vector, and well, we use label Rx to represent that, and Ry actually is y component. Okay, so if you know, we can, so basically, right, so we can use two methods to describe a vector. Either this one is magnitude and direction, or components, right? We can tell a vector by using its components. So you have Rx and Ry, a pair of components to describe this vector. Okay, so either magnitude, well, we use this symbol to describe magnitude, or direction, right? Right. So these are two components. Equivalently, we can use the components. You can project this vector into x-axis and y-axis. You get the components, okay, in x-axis and y-axis, and you can use these components to describe the vector. And the relationship between direction and magnitude, magnitude and direction and the components follow this equation. Okay, so you can tell they form a right triangle. You see, we just move the y components here, right? So this is x components, this is y components is here, but we can parallelly move to here. Nothing change. Okay, so x components and y components and the original vector form a right triangle. So I believe everybody here learned trigonometry before. If you forget about trigonometry, you can grab a pre-calculus book. Okay, in that book you have a really very good review of trigonometry. Okay, so you have a right triangle, and here is a theta, right? So AX is adjacent side of this right triangle, right? So adjacent equal to A. So this is the hypotenuse, right? We use A to describe to tell the magnitude of that vector. This is the magnitude of vector A. Okay, so I don't put any arrow on top of that. This tells you the magnitude. Okay, so we can tell adjacent equal to A cosine theta, and then opposite AY, right, equal to A magnitude sine theta. Okay, so you can tell this is how you figure out the components. Okay, so if you know the components, right, so I give you a vector, right, if I can give you components. If I give you components, can you tell what is the magnitude and the direction of the vector? Okay, so magnitude of the vector here is this. So from this equation, right, you can tell you square, right, you square this one, right? So ax squared equal to a squared cosine theta squared, ay squared equal to a squared sine theta squared, right? And then you add the two together, so you have ax squared plus ay squared equal to a squared cosine theta squared plus sine theta squared. Okay, cosine theta squared plus sine theta squared is identity, right? So I write here sine theta squared plus cosine theta squared is 1. Okay, you can actually prove this, but just memorize that. Okay, identity. So this equal to a squared, right? And then what is a? A equal to square root of ax squared plus ay squared. Okay. So if I give you components, then you should be able to know the magnitude of vector and also direction vector. So what is direction vector? So from this right triangle, right? So from this right triangle, we know tangent theta equal to ay over ax, right? So what is direction? Theta equal to arc tangent. Well, arc tangent, right? ARC, arc tangent ay over ax. Or you can write this way, inverse tangent function of ay over ax. Okay, you see, this is equivalent. If give you magnitude and direction, you can figure out the components. Or if give you components, you can figure out the magnitude and direction. So there are two ways to describe a vector. Okay, give you example. So if let me give you example. I write here. If I give a vector, right, the vector A, magnitude 20 meter per second. We can tell this is a velocity vector. Direction, theta, I gave you 60 degree. Okay, you know vector is this, right? So this basically is a vector, right? 20 meter per second. And this is a 60. And you go this way. Okay, so what is the vector's components? So this is vector, right? X and Y. So AX equal to A cosine 60. Okay, equal to 20 times, well, cosine 60 is 0.866. Okay, so if you have a calculator, oh, I hope everybody really know how to use a calculator, right? So when you use a cosine, make sure you use angle as a degree, not a radian. Okay, you can use a radian or degree. Okay, so there is a sign, there is a button in your calculator, tells you is a degree or rad. Okay, you choose degree. Okay, so if you choose the right angle, right, the way you describe angle, then you can just type in 60 cosine. Okay, degree, right? 60 cosine. Then this give you the right value, right? 60 cosine will be, 60 times cosine is 0.5. I'm sorry, I get it wrong. So 0.5, right? So this is 10 meter per second, right? So what is AY? Sine 60 actually 0.866. So equal to A sine 60, right? Equal to 20 times sine 60. 60 sine 0.866. Okay, so this equal to 17.3 meter per second. Okay, so that is can tell this components, right? This is the components and this x components, y components. Okay, so this is one example. I'll give you another example. So I know there is a vector, vector b, right? Bx equal to 5.0 meter per second, right? By equal to negative 7.0 meter per second. Okay, so what is the magnitude and the direction of this vector? All right, so we know that is components, right? So if you draw the coordinate system, right? So what is your x component? X component is here, wow, right? So bx, this is the bx. What is by? By is negative 7, right? So this is by. Bx, by. And what is b? B is bx, by. This is b. You see that? So by here you can parallel to move to here. So you form a right triangle, right? So you have x components, right, and y components. You form a right triangle, right? You see, x component, y component, you have a right triangle. Okay, so what is your magnitude b? B equal to square root of bx squared plus by squared, right, equal to 5.0 plus square plus negative 7.0 square, right? And what is this? So this will be 8.60 meter per second. That's the magnitude. Well, let's use for the problem, right? Let's use three significant figures, right? So I have 3 digits basically. Well, if the value is really big, right? You can, so if the value is 21704, how to make this 3 stick figures? Okay, so what you do here is equal to 2.17 times 10 to the power 4. So use scientific notation to tell this value. So there's still 3 stick figures, right? All right. So this is the magnitude of this vector b. And what's the direction? direction equal to inverse tangent function of by over bx, right? So inverse tangent of by is negative 7.0, bx 0.5, right? So 5.0, and you look at um, 7 divided by 5, and then you look at your inverse function, and in your calculator you have inverse tangent function, right? So in my calculator is negative 54.5 degree. Okay, so you can tell this angle, right? This angle is negative 54.5. Okay, so for B, right? So you have BX, BY, and this is B. So this is BX, BY, and the angle here, remember this is clockwise, rotate to the vector. So this is negative 54.5 degree. Okay, so if I give you components, you can find its direction and magnitude. Okay, so those two methods equivalency is equivalent. Okay, give you one, you can figure out another one. Give you so you can always know, you can always represent the vector by those two methods. Little bit problem. Problem here is you have inverse function, right? So when you do inverse tangent function, tangent uh, tangent tangent a tangent y over x, right? Tangent we'll say by b or bx, right? Well, if you use a calculator, inverse tangent function always return, well, basically the range of inverse tangent function is from negative 90 degree to 90 degree. That's a range. Okay, domain is it's a relative domain, right? So or relative value, okay, any value, okay, is a domain. However, range is negative 90 to positive 90. Okay. However, our angle actually is from the angle can be, well, if you use a clockwise rotation. Remember, if you let's use a counterclockwise rotation, counterclockwise, right? So this is counterclockwise. Then you get a positive angle. Okay. The range here is from negative 90 to positive 90. However, your range, if you use a counterclockwise rotation, right? So you can from 0 to 360. Okay, so that's your range. Okay, however, the inverse tangent function gave you, well, inverse tangent function gave you this range, right? So how to make the right one? Right one come from this. You have to look at the sign of the a, y, and ax. If the angle fall into the first quadrant, okay, so this, right? AY, AX, both of them positive, okay? And if you do an inverse function, get a positive angle in the first quadrant, right? And then you have to go back to check your sign, AY and AX. If both of them positive, you know the angle, whatever angle you get from the inverse tangent function is right angle. However, they can also be the third quadrant. Okay, so third quadrant, both of them negative, right? AY, AX negative, negative. So assume the example here is, assume there is example, right? AY is 7.0, AX is 5.0, right? So the ratio here is 1.40, right? So you do inverse tangent of 1.40, they come with a positive value, right? So 54.5 degree. Okay, then you see that is a right angle. If then you check both of them positive, that's right angle. Well, what if AY equal to negative 7.0, AX equal to negative 5.0? Okay, so in this case, the theta equal to tangent inverse Okay, so still equal to 1.40, right? You get a 50.4 degree, 54.5 degree, right? And then you go back to check the sign of AX, AY. Both are negative, which means they should be in the third quadrant. However, your angle is the first quadrant. Then what you do here is you have to add 180 to push the vector to third quadrant. Okay, so 54.5 degree is here. You have to add 180 to make the vector in the third quadrant. Okay, so this will be 234.5 degree. So this is 234.5 degree. Instead of 54, you go to 234. Same idea about the other two quadrant, right? Usually you have for the fourth quadrant you have AY negative, AX positive. Same example, this example, right? So you use a calculator, you get negative 54, right? So this will be negative 54 degree, right? So this is right. Okay, so this is a fourth quadrant. You check your sign, this is right. However, if it is in the second quadrant, right? So in this case, AX is, assume, right? AX is negative 5.0, AY equal to positive, right? So if you do the inverse tangent function, right? So that is 1.40, and this is negative 54.5 degree. Okay, and then you go back to check the sign. It turns out it should be in the second quadrant, and this angle is in the fourth quadrant. Okay, so what do you do? Same thing here. You add 180 to push this angle into the second quadrant. Okay, so add 180, right? So this equal to 125.5 degree. Okay, and then that is in the second quadrant. So this is a 125.5 degree instead of negative 54.5, right? However, this one, if you can use also this positive angle, right? So negative 54.5, actually this is 305.5 degree positive. Okay. So when you do the inverse tangent function to find the angle, be careful. You have to know which quadrant the vector should land on, and you have to adjust your angle accordingly. Okay, so first quadrant, the third quadrant, first quadrant and fourth quadrant, no problem. Second and third quadrant, remember to add 180 degree. Okay, so that's about vector. So we can use magnitude and direction or components to describe a vector. Okay. All right. So now I hope everybody's really comfortable with this method. Okay. Either way, right? Okay. Now let's look at how we add and subtracting, adding and subtracting vectors. Okay. Example here, this. So if assume, right, you have a series of steps, right? So you start from this location, you move 5 paces to north, and then you move 3 paces to east, and then you move 4 paces to southeast. Okay, so basically in the whole trip you have 3 segments, right? So 1, 2, 3. Ask you what is net displacement. We know displacement always start from the beginning, assume beginning here, right? And at the final location. Okay, so this is initial location, final location, right? And you draw line, link them together, and put an arrow here. Arrow is from the starting point to the ending point. Okay, so this is your net displacement. And what is this net displacement? This net displacement, actually, you have three vectors put together, right? So because you have three trips, right? One trip, second, third. This is A, B, C. Okay, so this is called D, or resultant. Let's make a resultant. This vector equal to A plus B plus C. Okay, same thing here. If you want to go to library, right? So if I ask you where's the library? Okay, well, library from here you go 2 miles north, and then a mile this one, right? And another mile this direction, right? So assume there's no direct route, right? You have to go by 3 routes, right? And then maybe here, right? So this is library. Okay, if we go through these routes, what is the net displacement? Net displacement actually is this. Okay, so this is displacement. Within this, in this trip, this one is your displacement, and this displacement you have add those 1, 2, 3, 4 vectors together, right? So A, B, C, D. Every vector contribute to your final vector, resultant vector. Basically, you add all together. Okay. So from this diagram, you can tell how to add a vector together. Well, here's how you add a vector together. So assume you have a vector A. Assume, right? Vector A, and you have another vector B. How do you add them together? Well, maybe you have a C. Well, let's just add A and B together, right? So here are two vectors. How to get vector C equal to vector A plus vector B. You can add them together in a graphic way. What you do here is you move the first vector, or you draw the first vector. This is A. You see this equal to that, or you can move A vector anywhere you like. Okay, so just move here, right? You draw the first vector, and then at the tip of first vector, you draw second vector. Draw means you just move the second vector parallelly to here. So the second vector, right? So this is resultant vector, or the sum of those two vectors is from the tail of the first vector to the end of the last vector. You draw a vector. Start from tail of the first vector to the end tip of last vector. And this vector is C equal to A plus B. Okay, so this is how you add vectors together. And this is how you add a vector together in graphic way. Okay, well, so you see, this is how you add a vector A, B, C, D, C together in a graphic way, right? So this one is A, B, C, D one by one, okay, in a graphic way. Graphic way is not that accurate, right? Well, it can be very accurate, but it's most of the time we use components way. So how to add vectors in a components way? Okay, so here I give you same thing, right? Let's make it give you 3 vectors. Give you vector A, give you vector B, give you vector C. How to add them together in a components way? For the components way, here's what you do. You figure out each vector's components. Represent each vector in a components method, right? So this is angle. So this is theta A, theta B, and theta C. Okay, so I give you magnitude and direction, right? So what you do here is you find their components first. So you represent them in the components. Okay, so we can tell AX equal to A cosine theta A, AY equal to A sine theta A. Okay, so this is A vector, B vector, Bx, By equal to B cosine theta B. This equal to B sine theta B. Okay, same thing here for C vector. Cx equal to C cosine theta C. Cy equal to C sine theta C. Okay, all right. So you first figure out, just use component to describe them. And I want you to figure out what is R equal to A plus B plus C, right? Then what you do here is you add all the X components together. The result when you add all X components together is your resultant vector's X component. Okay, so let's write one more step, right? So just A cosine theta A plus B cosine theta B plus C cosine theta C. Same idea. You add all Y components together. Equal to A sine theta A plus B sine theta B plus C sine theta C. Once you know the components of your resultant vector, so what is the magnitude of resultant vector? Magnitude of resultant vector is R equal to square root of Rx squared plus Ry squared. And the direction, theta R equal to inverse tangent function of Ry over Rx. Okay, and you have to determine or check which quadrant this angle will be. Okay, so use this one, right? Which quadrant? Based on the sign, right? Both of them positive, or both of them positive first quadrant, both of them negative third quadrant. Ry positive, Rx negative second quadrant. Ry negative, Rx positive fourth quadrant. Okay, so you can figure out which quadrant it should be. And then you figure out what is the addition of the vectors. Same thing about the well, this diagram tells you why you can do the components way, right? So if you want to know C equal to A vector plus B vector, right? So here is A vector. You can figure out this is AX, right? B vector, this is the BX, right? You see, add them together. Add them together graphically. This is the C vector, right? This is the C vector equal to A plus B. And what is the X component of C vector? You see, this is the X component of C vector. This is CX equal to AX plus BX, right? So the whole thing here is CX. So CX equal to AX plus BX plus BX, right? And the same thing here. Well, why you have CY equal to AY plus BY? You see, that is your AY. Well, AY is here, right? And then you parallel to move to here, right? Okay, and then BY, right? So this is your BY. Okay, and this is a CY, right? CY equal to, this is AY plus BY added together is a CY. Okay, so this graph proves that you can just add all the X components together and add all the Y components together to find the resultant vectors X component and the Y component, right? X component and the Y component. And then once you know the components of vector, and then you can go to direction and magnitude of the vector. Okay. All right. What about subtraction? Subtraction. Well, subtraction also important because in physics we always want to know the difference, Okay, so what is the velocity? Velocity difference of the position over time, displacement, right? So difference position. And what is acceleration? Acceleration is difference in velocity divided by time. Okay, difference in velocity, which means you do a vector subtraction. Okay, so assume we have two vectors, A and B, and we want to know the subtraction. Here is your A vector, and here is your B vector. We know how to do A plus B, right? So what is A minus B? Well, A minus B, right? So D equal to A minus B. A minus B is a special case of A plus negative B. First, what is a negative vector? Well, this is a B vector, right? So what is negative B? If a B vector like that, negative means same magnitude, opposite direction. Remember, opposite direction. So this is B, this is negative B. You see, this vector and that vector, well, I didn't draw that exactly parallel. Okay, just assume they parallel, right? So they parallel, same magnitude, they point to opposite direction. Okay, so the direction here is theta. Direction here will be theta plus 180. Okay, so this is the theta, right? And this one, so this angle, the angle for the negative B is theta plus 180. That's the meaning of opposite direction. Okay, so if your angle here is 90, right? So this is 90. What's the opposite direction? Opposite actually is this direction, right? And what's the angle? Angle here is this angle, 90 plus 180. This is 270 degree. Okay, so if a north is 90 degree, 270 is a south. Okay, so the opposite. So this is a negative vector, right? So subtracting is basically a special case of addition, adding, right? So this equal to A plus negative B, right? And what is so you can add them together in a graphic method, right? You draw the first vector A. At the tip of the first vector, you draw the second vector, which is negative B. This is B, right? Negative B will be this vector. So the resultant vector is from the tail of first vector to the tip of last vector. So this is the vector D, which equal to A plus negative B, and which is A minus B. Okay, so that's how you do the subtracting. Well, you can do the subtracting in components method, right? Same idea. Uh, so what is negative b, right? Negative b, if this one you have a bx by, okay, negative b will be negative bx negative by. Okay, both of them negative. You see, this is assume this is a b, right? So this is bx by, right? And this one will be, the components will be negative bx, negative by. Okay, and so dx equal to ax minus bx, dy equal to ay minus by. Okay, or you plus negative bx, right? Then which means equal to ax minus bx, ay minus by, right? So that is your resultant vectors components. So in general, components method, right, you can just figure out what is bx and by, and you do subtraction here. Okay, so that's a little bit easier, right? So you can do, you have another vector A equal to D equal to A plus B minus C, right? So dx equal to ax plus bx minus cx. dy equal to ay plus by minus cy. Okay, so you can just do that directly. However, in the graphic method, you have to draw this way, okay? So A, negative B, and that is your resultant vector. Do the subtraction. All right, other than those two methods, right, we have a third method to describe a vector, okay? We call this a unit vector way, okay? First, what is a unit vector? Unit vector is a vector, okay, with the unit length. Okay, so there's a vector, right? So this is a vector, okay, and this vector, the length of this vector or the magnitude of this vector is 1. Okay, this vector we call this a unit vector. What's the purpose of a unit vector? The unit vector gives you the direction. Okay, so we can assume this is a unit vector point to that direction. We call this unit vector A. Okay, so this vector only gives you the direction. Okay, and uh, and a vector we can maybe that's too much. I will not mention that. So this is unit vector, right? And if you have x-axis and a y-axis, right? So what is the unit vector of the axis and the y-axis here is this. So we call this unit vector of x-axis and this unit vector of y-axis, right? And the label here is x hat, y hat. We always know, right? So if your x and y this way, build x, y this way, right? So unit vector of x is this. And this is unit vector of y hat. Always, okay? So now we can describe the vector by using the unit vector. Okay, so we know A, right? You can use magnitude and direction, right? Or we can use ax, ay to tell this vector. Okay, we have two methods, right? 1, 2. Third one, unit vector, right? So this is how you define unit vector of the x and the y axis, right? So a vector equal to ax x plus ay y. Okay, so we can describe a vector in the unitary vector way. This is x component times x hat, okay, and plus y component times y hat. Okay, so unit vector give you only direction. The length of unit vector is 1. Okay, so basically this term put together, what is this? This actually, suppose this is a vector, right? These two actually put together is this vector. You see, magnitude here, well, not a magnitude, it's ax, right? So real length here is ax, and then you give a direction, right? And then the real length here, right, is ay, right? So this ay, and give you a direction here. That is this vector. So a vector, right, equal to ax plus ay. You see, and ax equal to axx, ay equal to ayy. Okay, so what if the vector in the other quadrant, right? So assume this is your x and y, and this will be the third quadrant, A. Okay, ay, we know ay is negative value, ax is negative value, right? Both of them negative, okay? And so this vector, right, equal to ay, which is negative, times unit vector of y vector. Okay, so the whole thing is negative something. Okay, so when you times a vector, we'll talk about vector. Yeah, we'll talk about vector times later, right? If you do this, right, and which means this describe this vector, okay, and ax tells you this vector ax, okay, and we know this is negative, right? Negative, and then times unit vector only give you tells you actually the positive direction of x-axis. So this is the unit vector, right? X hat, y hat. This is the x hat direction, okay? And then you times a negative value, which means you flip the x hat direction, right? So that's this direction, because x hat in this direction. And you actually, ax here is a negative value. You actually point to the opposite direction of the x-axis, okay? So this is the unit vector way to describe a vector, okay? So what you do here is just like find the components, right? And then associate with the unit vector, then you give the unit vector notation for the vector, okay? By the way, unit vector actually is easier, okay? It's mathematically easier to add together a vectors, right? So if A equal to AXX plus AYY, B equal to BXX plus BYY, if C equal to A plus B, right? So what you do here is you just add all x together, right? So AX plus ABXX plus AY plus BYY. Okay, so here x and y, there are two different directions. You cannot just mingle them together. You cannot add them together. So everything with x hat, you add them together. Everything with y hat, you add them together. Okay, so you get this to describe the addition of the vector. So the C equal to this. So you can tell, use unit vector way, you can describe a vector at least mathematically easy. So now let's talk about multiplying a vector, multiplying by a scalar. Multiplying a vector by a scalar, okay? Um, so assume this is a vector A, right? So by scalar here is what is 3A, okay? 3A means you make the length 3 times, you make the direction same, okay? Because 3 is a scalar, right? Okay, and by the way, ax, ay actually is a scalar. So this is scalar, this is scalar. Okay, and you gave a unit vector to a scalar, you basically use the scalar to make the scalar a vector. Okay, so this is 3a. 3a means 3 times length of the a, but you maintain the same direction. Okay, negative 3a, which means same 3 times of the magnitude, flip the direction, okay? And assume same thing here, right? So this is B, okay? So what is half B? So this is like a dividing, right? Division. Half B means magnitude, you cut in half, okay? And what is negative half B? Well, that's the meaning, okay? Other than multiplying vector by scalar, Uh, I really want to introduce you the vector multiplication. Okay, so I give you here a little bit, introduce how to do the vector multiplying. Okay, so you have two vectors. Um, hmm, hmm, okay, all right. So if you have a vector A, okay, and you have vector B, how to multiply them together? Okay, there are two kinds of multiplying. A dot B. This is called dot product. There are two ways, right? Dot product. Another one is the cross product. You will meet them all this. You will meet all of them in this semester. What is A plus dot B? A dot B equal to magnitude of A, magnitude of B, cosine theta. Theta is the angle between A and B. Okay, so this is dot product. Okay, so what we do here is we bring these vectors together. Let them start with the same point, right? And you can tell every two lines, two arrows, you always have angle between them. So this is theta. Okay, and this is dot product. Dot product give you a scalar. You see, this is not, this is not, this is this is this is not a vector, it's a scalar. The meaning here, what is AB cosine theta? This one can describe as A cosine theta times B, or equal to A times B cosine theta. Okay, so those two vectors, you have an angle between them, right? So A cosine theta is this guy, right? And then this vector, and so basically you project A to the direction of B, right? And the times them together. You make their magnitude times together, okay? Or you can project B to the direction of A and you do the time. Okay, so that's what you do. That's the meaning of dot product. When we meet dot product, I will tell you which physical quantity is a dot product. I will let you know now. Work is dot product. Okay, so we will learn what is work later. Okay, cross product. Cross is A cross B. Well, if you do cross product, you have a vector. Okay, so what is this vector? So this vector you have, well, magnitude. Magnitude is magnitude of A, magnitude of B, sine theta. Okay, direction. So it's pretty easy, right? Direction is a right hand rule. So what is right hand rule? If you look here, right, you want to do A cross B. Use your right hand. Position your hand so that your all the fingers point to vector A. Four fingers point to vector A, right? Okay? Use your right hand. Okay? Point to A, right? And then you have to position your hand so you can sweep your fingers to vector B. Okay? So for this one, right? So this is A, this is B, right? So you point all the fingers, four fingers. So right hand, right, you have four fingers and a thumb. Okay, point fingers to the four fingers to the direction of A, and position your hands so that you can sweep four fingers to B. Okay, so if you can do this, well, sweep four fingers to B through this small angle, theta. Well, you can sweep from A to B by using this big angle or small angle, right? You pick the small angle. You always use a small angle. The angle will be less than 180. Okay? And you can sweep fingers from A to B, right? This is the sweep direction, right? Sweep 4 fingers. If we can do this, then the direction of thumb is the direction of the resultant vector, which is A cross B. So in this case, what is direction of thumb? Direction of thumb actually get into screen. Okay, so use the right hand, right? So let the fingers point to the vector A, and you can sweep those 4 fingers to B. If you can do this, then the direction of thumb is the direction of A cross B. Okay, and let's see, make it a C. C equal to A cross B, and this is the direction of the C. Okay, so what is the direction of the B cross A? We call it C prime. So still use 4 fingers, right? Point to B, first point to B. Then you can sweep from B to A. Sweep, right? So sweep will be, well, let's see, B, A, sweep. This way, right? So use the right hand, you can sweep from B to A through this small angle. Then the direction of thumb, okay? Direction of thumb. Well, in this case, direction of thumb is here, right? This is coming out of the screen, coming out of the pad. This is called a cross product. We will meet a cross product in chapter 11. Torque is cross product. Okay, TORQE, torque is cross product. Okay, all right. Now let's talk about vector. Okay, so we know how to describe a vector, how to present a vector. You have basically 3 methods, right? Magnitude direction, components method, or unit vector methods. Okay, 3 methods, right? They are equivalent to each other. And then we know how to find out components of vector. And from components, you can figure out what is the magnitude and direction. And also we learned how to add a vector together, subtracting vector, and multiplying vector by a scalar. And we learn dot product and cross product. Okay, I believe a lot of you have learned this before. If you never learned this before, that is really good chance to learn dot product and cross product. And we'll talk about dot product and cross product more later, right? Whenever we see the real physical quantities involve this. Okay, so now let's talk about how to use the vector to describe the motion. Okay, so in motion, position. Important, right? How to describe a position. So you see here is, if you're here, right? So you start from here, okay? And then you end at here. How to describe this position? This is the starting initial position. Final position. Okay, and how to describe this? Well, very easy. You build a coordinate system at your preference, right? So here's your coordinate system. How to describe this position? You use a vector. Okay, we call this a position vector. Position vector is a vector start from the origin to your location. Okay, so you basically link your origin and your location. together, right? It's a straight line, and you put an arrow there to make that a position vector. Okay, so this vector is your initial position. We call this Ri. So we use a position vector to describe the position. Okay, so final position, same thing here, Rf. Okay, and what is displacement? Displacement delta R equal to Rf minus Ri. Final position minus initial position. Or we can see, right, so if this one move around, right? So what is displacement? Displacement always you start from the initial position here. You end at the final position, right? So this is your displacement. And this one actually equal to Rf minus Ri. Okay, why? Well, you can do the reverse way, right? So what is Rf? Rf equal to Ri plus delta displacement, right? So you see this is Ri, and then there's displacement, right? And then you figure out the final position, okay? Or you can use what we have learned, right? The subtraction. So you draw the first vector here, right? So this is Rf. And at the tip of the first vector, you draw negative Ri. This is your Ri, right? So what is negative I? So this is your negative Ri, right? So this is negative Ri. What is your displacement, right? So this one is Rf minus Ri. You see, this vector and this vector, they parallel. Well, I did not draw that equality, but anyway, you know what I mean, right? Parallel. Okay, so this is your displacement equal to that vector. You can remember you can move vector parallel to anywhere. So this one equal to that one. Okay. Well, physical meaning here is this. This is your displacement. All right. So if we know the displacement, then we can figure out average velocity. So what's average velocity? You see, you start from here, and this is your trajectory, right? Then you move to here. And this is your initial position, final position, right? And the displacement always, right, is this is your displacement, right? And when you at T1, you reach P1, position 1. At time T2, you reach position P2, right? So by definition, average velocity equal to displacement over time. Okay, so the direction of average velocity will be the same direction of your displacement. Magnitude definitely different, right? So delta t here is, okay, let me write here, right? So VAV equal to delta R displacement over time, right? So this is RF minus RI divided by T2 minus T1. Well, actually, is let's use P. Let's use R2 minus R1, okay, or P2 minus T1, doesn't matter, right? So this is the displacement over time. And so the magnitude will be different, and however, direction of the average velocity will be the same direction as displacement, okay? And what about the instantaneous velocity or velocity, right? So you see, this is your average velocity. Average velocity if you bring the second point very close to the first point. Okay, so basically, the meaning here is this, right? So you draw a line tangent to this curve. Remember, this curve is your trajectory. It's not a position time graph. Okay, so this is trajectory, right? So this is average velocity. Average velocity, you make the 2 points really, really close to each other. Initial position, final position, very close to each other, which means you make the time interval almost reach zero. They're very close to each other, right? So end up with this is your average velocity direction if you make them really close to each other. And this is your instantaneous velocity direction. And this is your instantaneous velocity, or we call that a velocity. Direction, remember direction, this is not a magnitude, direction, okay? So direction point to there, and then magnitude, you have to do the calculation, okay? When you do the magnitude calculation, you have to incorporate time there, right? Remember, this diagram is your trajectory. The path is not position time graph. From this diagram, we only know the direction of the velocity, okay? All right, so from this trajectory diagram or this path diagram, right? We can tell the direction of velocity, right? And by calculation, we know the vector, we know the velocity direction, velocity, right? And then we can figure out the acceleration. Okay, so here, well, it turns out, right, at every point, velocity will be in the line, velocity direction will be in the tangent line direction. Okay, so velocity here will be here, velocity here, just a tangent line, tangent, right? Velocity here, direction will be like that. Magnitude, you have to do the calculation. Okay, and then once you know the velocity, you can figure out acceleration, right? So average acceleration is the changing velocity over time. At this spot, P1, right? This is your velocity. Well, we know we have calculation. Well, we know this is velocity. At P2 or final position, this is your velocity. Okay, so we know at here is a T1, you reach here, T2 reach here. At time T1, you reach there, time T2, you reach here, right? And then we know the velocity, right? So what's average acceleration? Average acceleration equal to Vf minus Vi divided by Tf minus Ti, or T2 minus Ti. So this is average of acceleration, okay? Assume this is your initial velocity, final velocity, right? You do the subtraction, and then you can tell this is your changing velocity direction, because you see, Vi plus changing velocity equal to Vf, or Vf minus Vi is this. This is your changing velocity direction. And in the same direction of your changing velocity is your acceleration direction. And what divided by time, right? So your acceleration will point to this direction. So this is the average acceleration direction. Okay. So velocity vector is always in the direction of the motion. Okay, you see? Motion just like this. This is the first point, the second point, third, fourth, right? So from this sequence, from 1 to 2, 2 to 3, 3 to 4, right? So velocity here is this, in the direction tangent to that curve, right? So from the path, you know the velocity direction, right? Acceleration, you have to make the calculation. Acceleration in this here, right? So acceleration at this point, you have to bring the second point really close to here, figure out the velocity, right? And then you do the subtraction. It turns out acceleration will be in this direction. And here, acceleration be in this direction. So acceleration can be any direction, okay? Velocity always along the trace, along the path of the motion, always in the direction of the motion. Acceleration can be anywhere. You have to make the calculation, because acceleration, remember A equal to, you have to make the time really close to each other. Okay, make a time interval very small. And so this direction can be any direction. Okay, we have to do the calculation to figure this. Uh, Well, we will learn this more when we talk about the two-dimensional motion later, right? So this basically is two-dimensional motion. Okay, so position is a position vector, and the displacement, the difference in position, velocity is displacement over time. Well, you have average velocity, instantaneous velocity, and acceleration, changing velocity over time. Okay, all right. So now let's talk about relative motion. What is relative motion? All the motion, all motions are relative, right? Relative motion, you have a multiple reference, you have a more than one reference frame. Okay, example here is this, right? So there's a train, there's a guy stand on the platform of the train. There's a platform, right? Platform. Another guy actually is on the train which is moving. Okay, assume in this case, train move relative to the platform 15 meter per second towards east. Okay, and a guy, the yellow shirt guy, right, on the train move 1.2 meter per second relative to the train. Okay, then to this blue shirt guy, what is the speed or velocity? What is the velocity of that yellow shirt guy? Okay, well, you have to, it's different, right? Definitely, right? So the velocity of the guy, yellow shirt guy relative to the train is 1.2 meter per second. Well, by, intuition, you can tell the yellow shirt guy, the velocity of yellow shirt guy relative to the guy standing on the platform is, you have to do the addition, right? You have to do the vector addition, okay? So 15 meter per second plus 1.2 meter per second, right? So this is a 16.2 meter per second towards right. Well, if this guy on the train actually move backwards, okay, so in this case, 15 meter per second, right, plus negative 1.2. So this yellow shirt guy relative to the platform is this. Okay, so 15 meter plus negative 1.2 equal to 13.8 meter per second to positive right towards right. So that is this yellow shirt guy's velocity relative to the blue shirt guy, which is stand on that platform. Okay, so you have two reference frame. One is Earth, right, or the platform, okay, or the train station. Another one is a train, right? So you have to figure out what is relative speed. Okay, so here is the equation. So the subscript here is person relative to the ground. Velocity of the person, well, basically it's a yellow shirt guy, relative to ground, right, equal to, okay, so let me write a little more, right? So VPG is velocity of the person relative to ground. Okay, VPT is velocity of the person relative to train. Okay, and then VTG is the velocity of the train relative to ground. Okay, so here is what we want to know, right? The velocity of the person relative to ground equal to velocity of person relative to the train plus the train relative to the ground. Okay, remember this is a vector addition. Okay, so you see the first case, right? Velocity of the person relative to train, 1.2, right? So 1.2. plus relative velocity of the train to the velocity of train relative to the ground, right? So that's 15. So you see 1.2 plus 15. So the resultant will be this one, right? So this one is the velocity of the person relative to the train, this, right? Add train to the ground, okay? And then the resultant will be this one, right? The resultant will be starting from the tail of the first and at the tip of the last. So which is basically you do the subtraction here. Basically you do 1.5 negative, right? Plus 15.0, right? So equal to 13.8. One dimensional, this is basically this is one dimensional, right? You can use positive sign, positive, negative to tell the direction. So for this case, right? So this case is relative velocity of the person relative to train 1.2 positive, right? Plus 15, right? Train relative to the ground, right? Equal to 16.2 meter per second. Positive, which means the velocity of the person relative to the ground is 16.2. Okay. All right. This also happened to the two-dimensional, right? So if this guy is clamped up the train, so this is the velocity of the person relative to the train. So what is the velocity of the person relative to the ground? Okay, so here, so person to the ground, right? So here is the velocity of the person relative to the train plus the velocity of the train relative to the ground. So add together. So this is the velocity of the person relative to ground. So this is person relative to train, train relative to ground. This would be the velocity, okay, of the person relative to the ground. So just add them together. All right. I give you some real-time example. Example here is this. Suppose you drive in the rain. Okay, so here's your car. Okay, you drive in the rain. Okay, and this is ground, right? So you drive 20 meter per second towards east. Okay, meanwhile the water coming, there's a rain. Okay, so the rain coming down from the sky. Okay, so the velocity of the rain, well, relative to ground is this. Okay, so this is the velocity, so we call it v, rain to ground, relative to ground, right? And say this is velocity, okay, car relative to ground. Okay, so now I want to figure out what is the velocity of the rain relative to car. Okay, so the question here is, what do you see the rain from? So when you drive, right, you can tell, experience, you see the rain just right towards your eyes. Okay, so to you, the rain actually is this way. Rain just like tilted to you. It's a rain not just from the sky direct down, right? It's down with an angle. Basically, it's like just like a fall towards you when you drive this way. How we get this? Okay, very important. If you know what is the rain relative to the car, velocity of the rain relative to the car, right? Equal to velocity of the rain relative to the ground plus velocity of the ground relative to the car. You see, in this diagram, you have a loop. Person relative to ground equal to person relative to train plus train to ground. You see, person to train, train to ground. Okay, so you have to make a closed loop. Person to ground equal to person to train to ground, right? So same thing here. What is the relative velocity of the rain to ground, rain to car, right? Equal to rain to ground plus ground to car. Okay, so now what is the ring to ground? You can tell this is a ring to ground. Okay, so this is the VRG. And what is ground to C? Ground to car. And what do we know here is a ground to car. Car to ground is this, right? Then what is the ground to car? If a car to ground is this, okay, so you think a car is moving, ground is stationary, right? So you think the reverse way. Assume car is stationary. What is the ground velocity? Okay, so if you consider car is stationary, right, the ground will be, so okay, car move towards the right, right? Relatively, ground move towards left. If you consider car is stationary, then to the car, ground move to the left of the car. Okay, so this will be VGC, ground relative to car. Okay, so we have our velocity of RG, right, at GC. So this is GC, ground relative to car. Okay, and then what is your velocity of the ring to the car? Well, addition, right? So this is the velocity of the ring relative to car. Okay, make sense? So that's an example. Well, if you drive really fast, right? Really fast, assume the speed of ring is a kind of constant, right? Just like that. And this is really big, right? You drive like you almost flying, right? It's huge velocity. Then the ring just really tilted. Okay. Well, if your velocity is very small, right? The ring almost from the top, and you stationary. You don't have any velocity, right? So the ring, and you only have almost no velocity. You walk in the ring. Okay, so you can tell ring is almost pull from up, right? Okay, so this is a relative motion. Okay, I think that's all for this chapter. Okay, relative motion, a lot of interesting things later developed from this relative motion. Okay, Einstein, Einstein's relativity basically from relative motion. Okay, and he developed relativity means relative motion. It's not a motion. Okay, so just as the ground is a coordinate system, right? So this is a ground coordinate system. A car move also with a coordinate system. So this is x, y. So car move with another x prime or y prime. Okay, and then you have two coordinate system. Okay, so we have to use something called the Lorentz transformation to apply to this two reference frame. And from there, Einstein developed that length contraction time dilation. Dilation means longer, okay? Time dilation and length contraction. What's that mean? Which means if somebody in the car, okay, if there is a ruler in the car, right? So to this reference frame, to the person in the car, you see that's a ruler. The ruler is maybe yard meter, it's like a meter stick, right? So that's a meter. However, to the person on the station, it's shorter than 1 meter. Okay, so that's a called length contraction, and time dilation means the time move forward with a different pace. Okay, anyway, that's a very complicated. So I hope some of you will learn relativity later. Okay, when did Einstein figure this out? 1905. Okay, so it's already more than 115 years ago, right? People figure out that. Okay. That's a relativity, but the idea comes from a relative motion. All right, so that's all for this chapter. So make a summary. This chapter we learned a scalar. What is that? Number with unit, right? And vector. Vector is magnitude and direction. Okay, and to describe a vector, we can use the components way, how to figure out the components of vector. And once you know that this is the components, right? If you know the components, you can figure out the magnitude and direction. And also we use the graphic way to add a vector together, right? And also we use the components way to add and subtract vectors. Um, and also we learn the unit vector notation, right? Unit vector way to describe a vector. Um, and that's all for the vectors, right? Then we learn how to describe motion by using vector, right? So we use a position vector to tell the position. And then displacement basically is the difference on the position vector, difference on the position. And also we know the velocity vector's direction, okay? Um, and at the last, and also we learn the acceleration vector, okay? And at last we talk about the relative motion. Relative motion, this is the equation, okay? Velocity of the 1 relative to 3 equal to velocity of 1 relative to 2 plus velocity of 2 relative to 3. Okay, so that is relative motion. That's all for this chapter. Okay, if you think it's very hard, read the book, email me. Okay, email me. Just feel free to email me. I'm here to help you. I'm always available. We can have if a question is simple, I will answer you directly from email. If a little bit complicated, I will set up a Zoom session to discuss this with you in detail. Okay. All right. Have a good time. See you next time.